Now let's take a look at the last two basic gates, those being the exclusive OR gate and the exclusive NOR gate. So the first one is called an exclusive OR gate, also called an XOR gate, and the symbol for this, for a two-input version, is going to be similar to an OR gate, with the exception that it's going to have two curved lines on the left-hand side. So that right there is the exclusive OR gate symbol. The truth table for an exclusive OR gate, let's call the inputs A, B, and the output F, is going to look like this. So for A and B is equal to 0, 0, output is 0. For 0, 1 and 1, 0, the output is going to be a 1, and for 1, 1, the output is going to be a 0. So you notice that the output is asserted whenever the two inputs are different from each other. And this gate is also called a difference gate because it asserts whenever you have A and B different to each other, and it is unasserted whenever A and B are equivalent to each other. So the two-input version of an XOR gate is often referred to as a difference gate. Now, if you look at the logic expression for this, we define a new algebraic operator, and that is like this. It's the same as an OR gate expression, except we put a circle around it. So this right here is the exclusive OR gate operator. Okay? So this is a very simple gate, and it kind of rounds out all the possible operations that you can have for a two-input binary code. However, if you look at the formal definition for an exclusive OR gate, it scales. If we were to look at a three-input version, so A, B, and C, it isn't a very useful gate once you go above two inputs. So if I was to come along and write what the truth table would be for a three-input exclusive OR gate, I would have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1. And then I would have 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And if I use this textbook definition of a difference gate, or the theoretical definition as a difference gate, what would happen is that it would be unasserted for 0, 0, 0, and for 0, 0, or for 1, 1, 1, and then for all other input conditions it would be asserted. So this means that the truth table would look like this. Now this turns out it's not a very useful gate when you have a situation like this, and it also turns out that it's a lot easier to make this type of truth table output using a combination of other gates. However, a more useful definition of a three-input exclusive OR gate is to use a cascade of two-input exclusive OR gates. So this right here is the textbook, or kind of the mathematical correct output, but we don't use this in practice, so this is something that we don't use. What we do, however, is we use a cascade of two-input exclusive OR gates, and what we would have here is an exclusive OR gate here, an exclusive OR gate there. And what we would do is we'd say A, B, and C. And what we would do is we bring in the inputs as such. So notice that you have a cascade of two-input exclusive OR gates. And if you walk through the truth table for this, what ends up happening is you'll see something that looks like this. You'll have A, B, C, and F. And you will have 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. And the output will actually be this. It'll be 0, 1, 1, 0, and then it'll be 1, 0, 0, 1. It turns out that this truth table right here has a lot of practical applications. First of all, it is used for addition, because if you think about it, if you added A, B, C in together and produced a one-bit sum, this truth table would in fact give you the one-bit sum. And it turns out that three-input exclusive OR gates are used quite frequently in binary adders. Another reason that this is important is for error code checking, because if you look at what's happening here, in addition to being a 3-bit input adder, you can also use this to count the number of ones. So this will actually assert when you have an odd number of ones. So it will assert when you have an odd number of ones. So for example, if you look at row 1, you had 1, 1. So that means that you had an odd number and it asserted. Row 2, so if you put the row over here, you'd have 0, 1, 2, 3. Row 2 was also asserted. Notice that on row 3 you had an even number of 1s. Well, that turned out to be unasserted. And then if you look at row 4, you had an odd number. Row 5, 6, and 7, 5 and 6 you had an even number, so it wasn't asserted. And then 7 you had an odd number again. Turns out that this is used in an error correction called parity checking, and it can be something that you can use this circuit to actually generate an error detection bit and send along with the original piece of data, and then the receiver can look at it and say, oh, you wanted to have an odd number of 1s in that code. I will also check the parity code and verify that you did have an odd number of 1s, and if you did not, I'll have you resend that. So the point here is that if you go purchase a 3-input OR gate in an actual part, it's going to be implemented as a cascade of 2-input exclusive OR gates, and not the actual mathematical definition as a difference gate. Okay, so if we look at its inverted version, you're going to have an XNOR gate, and this operates exactly as all of our other basic gates, where you're going to have an inversion on the output. So it's simply an exclusive OR gate with an inversion bubble, and the truth table for this will be A, B, and F, and it will be exactly what a 2-input exclusive OR gate is, except that the output will be inverted. So in this situation we would have, instead of being 0, 1, 1, 0 like over here, you'd have 1, 0, 0, 1. Now if you look at this, sometimes this is called an equivalence gate, because it will be asserted whenever A and B, or whenever the inputs are equal to each other, and it will be unasserted when they are different. So they're actually, you have a difference gate as a XOR gate, and the equivalence gate is a XNOR gate. That only applies to the 2-input versions. If you continue to scale this to the 3-input, it will look exactly like the 3-input version of an XOR gate, except with an inversion on the output. So you would have the 3-input version here, and you would simply invert all of the outputs. So you don't have to really think about a cascade of 2-input XOR gates. All you have to do is think about what the output for a 3-input XOR gate would be, and then invert it. So your outputs would be 1, 0, 0, 1, and then it would be 0, 1, 1, 0. The logic expression is going to simply be F is equal to A exclusive OR with B, all inverted, or you could put it another way, A exclusive OR with B in parentheses and then not it. So those are the last two basic gates, and that rounds up all of the lowest level computational operations that you can do on a 2-bit binary code.